Welcome, everybody. Only two very brief announcements. There's a homework due this week, as usual. You can turn it in early this week for bonus points, as usual. And project 2 is due on Friday. Will, is there anything else that we should be pointing students to? I think we're fine. We'll talk about next week in a day or so.
No, I think that's good for now.
Thank you. Right. So this week and part of next week is, well, actually much of next week is going to be devoted to the topic of prediction, in particular, predicting one numerical variable based on another. Last time our discussion was focused on developing a measure of linear association. That's the thing called the correlation coefficient. And today we are going to use that quantification to make predictions of one numerical variable based on another, provided some particular conditions are satisfied. And on Friday, you will begin to see why, in what sense that is the best. And hopefully by that analysis, you will be able to extend that method of prediction to situations where the relationship is not linear. So a quick recap of where we were. The correlation coefficient is a number that measures linear association, that is how clustered the points on your scatter diagram are about a straight line. It does not measure all kinds of associations, specifically for linear association. It's a number between -1 and 1. We just told you this as a fact. And the extremes correspond to perfect straight lines. The sign corresponds to the sign of the association. Positive meaning above average values of one are typically associated with above average values of the other. Below average values of one are typically associated with below average values of the other. R equals 0 is no linear association. And that is what uncorrelated means. This is much weaker than unrelated. Unrelated means no relation at all of any kind. But uncorrelated just means no linear association. And with that in mind, actually, before we go on, those graphs there, what we have done is we have generated data randomly to give you scatter diagrams that have correlations that are very close to those that are listed on the pictures. So this, the extreme right, where it says R equals -0.5, it might be a -0.501 or something, but it's close. So one thing to keep in mind is that if somebody just shows you a scatter diagram, it's actually not so easy to tell what the correlation is, because it really, your eye is very much affected by the scales on which these pictures are drawn. But if you have multiple pictures on the same scale, as you have in this case, then you can at least compare, right? So that this formless blob, no linear relation, R equals 0 seems perfectly reasonable, whereas compared to even here, you can clearly see a positive association and a much stronger one here. The last one is a negative association. Okay, so with this in mind, let's go through what correlation measures. It measures linear association. I will take you through the formal definition. You convert both the variables to standard units. Why? Because we noticed that whether or not something's clustered about a straight line, we can see that in the picture without actually paying attention to the precise numbers on the two axes. That is a signal that we can work in standard units. The exact units of measurement don't matter. So we'll work in standard units. And it turns out that if you multiply these, and we went over a reason for that last time, then and take the average of the products, then that gives you your correlation. And once again, this measures how clustered the scatter diagram is around a straight line. And so I have a question for you. True or false? If the correlation of X and Y is close to 0, then knowing one cannot help us predict the other. Think about it, post your answers or your thoughts in the chat. A bunch of people are saying false. A bunch of people are saying false. Okay, so we're getting false. And so could somebody, Tony there has the reason. So we have, well, actually, no. That's a reference to a book. I don't know. Yes, so false because you could have a nonlinear relation. You can have a very strong nonlinear relation, in which case you can predict y from x almost perfectly. And so I'm delighted that you have all picked up that not correlated does not mean not related. Okay, terrific. And so why don't we now move to some things that you know to watch out for. You know that correlation is not causation. You've known that association is not causation since essentially lecture 2 of this class. You know clearly very well that you should watch out for nonlinearity. If you have a nonlinear scatter diagram, the correlation is not a good measure of the association. You saw last time that outliers can have a drastic effect on the correlation. We had a perfect straight line and then we broke it by 1 point and the correlation went from 1 to 0. And typically it isn't that extreme, but there is outliers do affect correlation. So what should you do if you have an outlier? You should look to see why that thing is an outlier, right? If it's just that you mistyped something, then fix your error and redraw your scatter diagram. But often outliers are very interesting points, right? You understanding the reason why they're all the way out there helps you understand your problem. It's possible that you can study them separately. What you should not do is just drop them and say, I'm going to study all the others. Or if you do that, at least you should say that, but come back and do study the outliers. Okay, so there's one other thing to watch out for, and these are called ecological correlations, which I will show you in a demo. And today's demo, please run the import cell. And then run this long cell where we have written a whole bunch of functions that will plot things. You don't have to know what the code is there. It just helps us show you some graphics in the demo. The definition, the conversion to standard units is a function that we have written a couple of times. And last time we said, okay, once we have a function that converts an array to standard units, then we can convert each of 2 arrays to standard units, multiply the standard units and take the average, and that will give us the correlation. So correlation is a function that takes a name of a table and the labels corresponding to your 2 variables, and then returns the correlation between those 2. So let's run these 2. And now I want to show you data on SAT scores from 2014. And these are SAT scores by state, right? So there are 50 states and DC. So for each state, there are a bunch of variables, and we are going to be focusing on these 2. The critical reading number is the average critical reading score in that state that year. And the math number is the average math score in that state that year. And I would like to look at the relation between the critical reading and the math scores. And so we will do our usual thing, which is to visualize. So we draw a scatter diagram. And that is stunning. Look at that. Linear, but I mean, linear that is almost, forgive me, but ridiculously linear. I look at that and I start wondering about what this picture is telling me, because it seems to me, not only is it linear, it seems to me it's almost the x equals y line, right? And so basically what this seems to be saying is that if you know the critical reading score, then you know the math score, it's almost exactly the same, but that's got to be nonsense. Do you agree? I mean, if you think of all the people, yes, you can quote me on that one, Professor Adhikari, ridiculously linear. If you think of all of the people that you know that take these tests, now, of course, you know a very rarefied section of the universe because you are all Berkeley students, but if you think about the people who take these tests, do you think they're all going to be perform exactly the same way in math as in, oh dear, somebody was very bothered by the SAT. Yes, well, we've gotten rid of it. But do you think they're going to perform the same way in math as in critical reading? No, you would expect that they are positive related, but this is, as I said, ridiculous. What's the correlation on this picture? The correlation is 0.98. This something is the matter here. All right. And so the thing to do is to notice that what we are doing is we are looking at the critical reading and we are looking at the math, but what we need to do is look at what these points, who these points represent. And does each point represent a person? No. So each point represents a state. Okay, question to you. Do states take the SAT? They do not take the SAT. All right, so this picture is all very well. It is a correct picture, but to use it in any way is rather complicated, because you have to, actually it's very hard to know exactly what you're going to use it for, right? Because what you want to be able to do is for an individual student to talk about their relation between their math score and their critical reading score. At least you want to talk about a group of students and look at their math scores and their critical reading scores. So one of the things, actually, let me see if I can stop sharing this and do something on my iPad here. So we have a picture that is like this. And I'm just going to draw a few points. Okay, so this is a state. And so you have critical reading and you have math. Now, states do not take the test. Who takes the test? Well, people take the test. So let's have people in blue. And let me look at this state at the bottom here. If I plot the points corresponding to each student in that state, will they all be on that dot? The bottommost dot? They won't. They will be somewhere around that dot. I don't know exactly how, but they will not all fall in that dot. Okay. So what happened to that dot when you went away from the state and actually looked at the individual people? It became more fuzzy, did it not? And now if you play this game with every single dot, right? So this state, if you look at its people, I don't know how spread out they are. I'm just drawing a little schematic here. What is happening to this picture is if you look at these representing student, what is happening to the picture is that it is getting more fuzzy. Right? And so if I ask you then correlation between the reading and math for students, okay, over to you. Equal to 0.9847, less than 0.9847, greater than 0.9847, which? Yes. This is less than the correlation between state averages. Okay. And so these are what are called ecological correlations. An ecological correlation is one in which the individual for whom you are plotting a point isn't actually an individual. You have a bunch of individuals all of whose values have been grouped into that point somehow. And so what that does in this case, we had students, but then every student in a state has been lumped together into the same point of averages, like the average of reading and average of math. And by doing so, we have artificially created clustering. And so naturally, the correlation is higher. So this correlation 0.98747 is called an ecological correlation. You've got these sort of ecological groups of people on whom you've calculated the correlation. And this tends to be typically artificially high. So when you look at correlations, don't just look at the value. Don't even just look at the variables, but look on whom are those variables being measured. And that is pretty important. It's actually interesting to see why these state averages are so close to each other and they're so tightly clustered about a line. What is going on here? Who do you think is in the top states here? Better education, richest, these are very natural guesses. Rich people, states with more funding, that's what Massachusetts, you're saying. Okay, more resources, that's what we're saying. Well, I understand that guess. Those guesses are very, very natural. But the world is an interesting place. Let's take a look at the data that we have. So we have a bunch of scores. There's the combined score, which I didn't use. Fine, there's a writing score, which I didn't use. We're just looking at these two. There is something else. We have here the participation rate in each state. That's an important variable to consider. The participation rate in a state is the percent of high schoolers in that state who take the SAT. And that, as you can see, varies widely. In Connecticut, lots of people are taking it. Delaware and DC, some states actually require the SAT. Whereas in Alabama, it's very low. Okay, so what I'd like to do is I would like to connect this variable, the participation rate, with this scatter diagram here. So I have this third variable that I want to bring in. And so what I did was I wrote a function which is a crude categorization of this rate. I code these rates as low, moderate, high, and high. Just because I just want to, I don't want to look at all the detail. I want to look just in some categories. And I just said, look, the rate is a percent. So if it's less than or equal to 25, call it low. If it's above 25, but less than or equal to 50, then call it low moderate. If it is above 50, but less than or equal to 75, call it moderate high. And otherwise call it high. And this is just a choice that I made. You can make different choices. Okay, and what I'm going to do is I am going to apply this function to the participation rate column. So I'll take my table, I will apply the rate code function to the participation rate column, and this object rate codes that I have just created. What is that? Is that a table? Is that, what is it? Rate codes. If I run that, what is it going to be? It is going to be an array. It is going to be an array because that is what apply produces. It produces an array. Good, wonderful. It produces an array. And so what I'm going to do is I'm going to augment my SAT 2014 table with a column of these rate codes. So let's take a look. Okay. So Alabama had just a 6.7% rate, and so it comes out as low. Delaware 100% is high. California 60.3, greater than 50 is moderately high. And so now you see that we have our coding here. And now I'm going to do something that I do all the time when I am analyzing data. We're going to redraw the scatter diagram. But we're going to use one of my favorite arguments to scatter, which is a group argument. And I'm going to group, what it does is it groups the data by the column that you specify, which in my case is going to be the rate code column. And then what does it do? Let's take a look at what it does. Aha. It gives me a different color for each value in the group. Right, so the lows are the yellows, the low moderates are the blues, which are very few of them. I can only see about a couple. The greens are the moderate high, and the black are the high rates. Okay, now look at that picture. Think about it for a second. What are you seeing? Who's at the top? Low rate. There's really no doubt about this whatsoever. It is the states with the low participation rates that are at the top. And, in about 10 days or so, you're going to start classification of points by properties. And this is about as clear a classification as you can get. And so what is very interesting, I think, is to see who had the low participation rates. And why don't we take a look at who those are? These are the states with the low participation rates. Okay, Alabama, Arkansas, a whole bunch of these states. Okay, now everybody who said that, oh, these are the rich states, these are the states with high educational, with a lot of high educational standards, a lot of money, resources for education. What do you think? Is that consistent with what it's the opposite? Almost the opposite, because there are many states here which are not very well resourced compared to others. So low participation rate are the highest points here. No, they actually, every state reported every SAT score. Nobody chose to report or not report. But is it surprising though? Is it surprising? Let's think about surprising. Okay, good, I'm glad. I love it when data science surprises you. Why do people take the SAT? To go to which college? Community college? Four-year college. Four-year college that requires the SAT. All right. Now, which kind of student is going to do that? If you required your SAT to get to, well, okay, so the students who want to go into those kinds of colleges and who feel that they can go to those kinds of colleges are also typically the students who are doing very well in their classes. And so it's not surprising at all that if just those people take the SAT, that their average scores are going to be high. In states where, like California, where there's quite a lot of participation, 60% participation, you get more of a variety of scores, right? So you get the high ones, but then you also get some of the low ones that brings your average down. And so why don't we look at the states where participation is very high? Look at the states where participation is very high. Where are they on our picture? Are they high or are they low? They're near the bottom. The dark colors are down here. All right, and which states are they? Massachusetts has a very strong educational system. I think the number of colleges per capita are probably among the highest in the world. These states, Connecticut, Delaware, the participation rate is very high, but the average scores for the states are lower compared to the other states. Why? Because in every state, you will have the highest performing students taking the test. But in states where the participation rate is very high, you also have students who are not that high performing, who take the test, and that therefore that has an effect on the average. So what have we learned from this analysis? We've learned a bunch of things. First, when you look at a correlation and it's very high, you should take a deep breath and not get too excited. you should take a look at what are the individuals on which the variables are being measured. And so the first look that we took was, oh, these are states. Okay, there's already a problem there. The second look that we took was even more careful. It said these are not only these states, these are a selected group in the states. This is not every high schooler in the state. This is the group that took the SAT in the state. And that observation appended our opinion, right? And this is the power of very careful data analysis. We have done no inference here. We have just looked very carefully at describing the data that we have. So I'll go back to the slides. No, got to share the right screen. That was the right screen. I need to go back to the slides. Okay, I am a mess today. Those are my slides. Okay, so you know to watch out for ecological correlations. I'm going to show you an ecological correlation. It's beautiful. This was actually in a serious paper. The reference is at the bottom. This is a scatter diagram. It was in, okay, so each point represents a country. And they are, you know, represented by their flags. On the horizontal axis is chocolate consumption per capita, kilograms per year per capita. And on the vertical axis is Nobel Prizes per 10 million population. What are you saying? Are you seeing a positive association here? You're totally saying a positive association here. In fact, R is 0.79. Somebody calculated it. There's a 0.79. So how about we all go out and buy a whole ton of chocolate? Should we? Right? The Nobel Prizes are waiting. Right. Okay. So there's an issue here. There's an issue in which is that the countries don't eat chocolate and countries don't get Nobel Prizes. Unfortunately, people do. Somebody says dark chocolate is better. That was actually something that was half seriously noted by the physicists, but never mind. So let's look at the variables here. Okay, who's on top? Switzerland. What was the nationality of the people who wrote this paper? I believe they were Swiss. Okay, so shall we look at the variables? Chocolate consumption per capita. Maybe the Swiss eat a lot of it. They certainly make a lot of it. Maybe they eat a lot of it. How about the Nobel Prizes? Is it number of Nobel Prizes that they're measuring? What's on the vertical axis? It is not the number of Nobel Prizes. It is the number of Nobel Prizes relative to population size, right? Per 10 million population. Now, is Switzerland a big country or small country? It has a small population. So anytime you look at rate per capita, right? You're going to get higher rates in Switzerland. The United States has a ton of Nobel Prizes, but it also has a huge population. So when you look at number per 10 million population, it is lower, and China is just blown out of the water there. Okay, so when you look at a diagram like this, we're all amused, and it's a wonderful observation, but it's also important to know how to interpret it. What really amused me was that it came out in a serious journal, in a paper, and people were not sure whether to take it seriously or not. I think in the textbook, I refer you to some analyses of these, and people are not sure. I mean, do we write about this respectfully, or is it a joke? Anyway, so this is certainly an ecological correlation, and so you should be careful. Okay. Let us now move on to prediction. And I'll remind you of the prediction that you've already done. You have a scatter diagram that is oval-shaped, which means there's kind of a straight line going through it. This is kind of a positive association. We say moderate. What's considered moderate varies widely by subject area. So I don't think there are any standard rules there, but it's positive association. And so how can we predict the child's height from, well, this thing says mid-parent height, but we have the average height of the parents. what we did was we said, okay, so there's this new child and we know the parent's height. So what we're going to do is we're going to look at the parent average height and look at all the parents, the families that were close to that parent average, and take the average height of their children as our prediction. And if we did that for every single value of the horizontal axis, then we got something that looked very much like a straight line. And that was our approach to prediction. So this method of prediction, we are calling a nearest neighbor regression. And I will explain nearest neighbor now, and we'll talk about regression a little bit. Okay, so it's a method for prediction. So it says you are predicting, okay, so the variable that I will start with, I'm going to call X, and the variable that I'm going to predict, I'm going to call Y. This is a convention. You can do it the other way around. In that case, you have to rewrite the entire lecture. Okay, so you group each X with similar X values nearby, and you get to define what nearby is. And then you find the average of the corresponding Y values, right, for that group of nearby X's. So these are your nearest neighbors to the point for which you are trying to make a prediction. And you make K nearest neighbors is going to come. It's going to come. It's going to come. This is just nearest neighbors. I'm not determining how many nearest neighbors there are. I'm just letting the data tell me how many nearest neighbors there are. Okay. So for each value, our prediction is the average Y value for the nearest neighbor group. And so this graph of predictions, we will call the graph of averages, because every point is every gold point is an average. It is the average of the nearest neighbor group. If the association between X and Y is linear, then the points of these averages will tend to fall along a straight line. Okay. But if the association is not linear, this is also still a perfectly good way of making the prediction. It's just that the points won't fall on a straight line. They will follow whatever is the nature of the relationship between X and Y. So this is a very powerful method of making predictions. This does not rely on the graph looking like a straight line. However, if the graph of averages does look like a straight line, then it is very natural to ask, what is that line? Do I really have to go through calculating all the nearest neighbor averages to get that line, or can I just recognize what that line is? And so we'll spend the rest of the time trying to recognize that line. Okay, so if I look here, if I give you this scatter diagram, what units have I drawn it in? Yeah, in standard units, because you can see that that thing is linear. You don't need to know exactly what units the variables were measured in. Okay, so where would the prediction line go through here, do you think? Yeah, it's kind of Y equals X. This looks like a very reasonable candidate, maybe a little bit off from that, but the X equals Y line looks pretty reasonable. What about that? Other extreme, no linear association. Where do you think your prediction line is going to be? How are you going to come up with it? Why don't we just try to predict? Supposing my person is at -1.5, right? What's my prediction going to be? Well, I'm going to go -1.5. The Y values are kind of here to about here. What's the average? Isn't the average around 0? Yeah, so if I looked at X at -1.5 is looking to me that if I look at these values of Y, their average is around 0. So also if I look at X equals 0.5, then also, it's the graph is kind of symmetric about the horizontal axis here. So I'm looking at a flat line at 0. They're lines, right? And notice that we are just identifying them by slope. And so what we're going to do now is look at a demo where we're just going to run this kind of thing for multiple different values of correlation. So what we have done up way at the top on all those functions, we have defined R table is a function that takes a correlation and gives you back 1,000 data points with pretty much that correlation. It's empirical, so it's not going to be exact, okay, but it's going to be pretty close to 0.99. And so I'll draw the Scatter diagram, what resize window does is it makes sure that both axes are on the same physical scale. All right, so this is the picture that you saw, other than color, on the slide. And what we're going to do is we're going to do a nearest neighbor prediction. We're going to take some value here. We're going to look at all the points that are close to it. And we have just defined close to be within 0.25. You can make some different definition if you want. And then we are going to look, we are going to return the average Y value of those close points. So we're going to take an X value as our argument. We're going to look at all the close points and return the average Y value of those close points. And we are calling this NN for nearest neighbor prediction example. So if we apply it to minus 2.25, which is getting pretty much, it's coming out here, then our prediction is, okay, minus 2.14, not quite minus 2.25, but that's our prediction. So what we can do is we can do this for every value of X. And so we are going to do that by doing what? We are going to take our table and apply this function to the X column. This is exactly what we have done for the heights example. We're just doing this in this fabricated data set. And so that chugs for a while. And we visualize those gold points are the points of averages. And you can see that's pretty close to the X equals Y line. That is the line with slope equals 1. All of these lines are going to go through the center, so there's no Y-intercept. They're going to go through the origin, that is 0, 0. There's no Y-intercept. All right, so I'm just going to draw the line with slope equals 1 on top of this picture. And you see that's not bad, right? It's not perfect, but it's not bad. Okay, so here, what is the advantage of drawing this line with slope equals 1 is just because we don't have to do any group average calculations. We know how to draw a line with slope equals 1. Okay, we're going to play this game over and over again. Will we always get a continuous line from this? We are actually drawing the line. That line will be an approximation to the slightly bumpy histogram of points that you get. The points are not going to be continuous, right? But the line is a line, just an ordinary line. We are choosing, we defined close points to be those that are within 0.25 of our given point. Okay, question. What happens if we wanted to estimate other Y values with only the predicted Y scatter line? What do you mean? The game is, I'm going to give you an X and you're going to predict the value of Y. So if I gave you X equals 5, you shouldn't use this. You don't have data there. Maybe that's what you're asking. I'm not sure. Okay, so we're going to play this game with R equals 0 now, because that's, you saw that on the slide. I'm going to generate a table and draw the scatter diagram. I'm going to apply my nearest neighbor method for prediction. That is, close points are defined to be those which are within 0.25 of my given point. And once that's done chugging, we're going to draw this line. And what I've done is I've drawn the line with slope 0 over it. And you can see that's not bad. Where is it off? It's off at the edges. All right. Any kind of prediction that you do is typically going to be worst off at the edges. That is where you have least data. All right. So it's the most noisy, those regions. But around about the center is not that bad. Okay. Okay. So interesting. We have been able to observe this, that this line is 0, has slope 0. There's another number that we used that was 0 here. What was the number? What was 0 in here? Yes, that was what we gave as R. Yeah. And here, what did we provide as R here? We provided 0.99. We used slope 1. Could we have used slope 0.99? Probably. So let's try slope equals 0.5. See if this pattern holds. So there's a scatter diagram, slope equals 0.5. And so what we're going to try and do is we are going to try and predict the value of Y for X equals 1.5. Right? So we've just drawn you the vertical line at 1.5. And we've drawn you the red line, which is the x equals y line, so that you can roughly see where the points are. This is not, it's just to help you visualize. So what we are going to do now is we are going to use our method by applying our nearest neighbor prediction function to make the predictions for all the x's. And while that is chugging, what I would love for you to do is look at this picture and say whether you think our prediction is going to be here, where our black line intersects the red. Is that where our prediction is going to be, or is that too high, or is that too low? That point where the black and red lines intersect, is that where your prediction is going to be? It seems too high because I'm looking at the y values. They go from about here to about here, and that is not their center, right? The center is a little bit lower, right? So this is not the right prediction. We are not predicting on the x equals y line. We're predicting on some other line. And where are we predicting? Well, we're predicting on this line. So here's a line with slope 1, but our predictions are on a flatter line. Okay, and what do you think the slope of that line is? You just had to guess based on everything that, let's try slope equals 0.5. It was the correlation. Let's try slope equals 0.5. Slope equals 0.5 doesn't seem that bad at all, right? Now you might be saying, oh, well, maybe you should have taken 0.51, but 0.5 is not bad. Okay, you can see that. And so how did we know does the correlation equal to the slope? Isn't that the burning question? Why don't we see whether that works out in the case where r equals 0.7. So I'm going to play the same game with r equals 0.7. You guys are getting sick of this, but I think, this is the way patterns are discovered. And in fact, this is the way the correlation was discovered, by doing this kind of analysis. So I'm going to play the game with r equals 0.7. Why is it taking a while to chug? Because it is doing the nearest neighbor prediction for each value of x. And once it's done chugging, it will, r equals 0.7 was pretty good. Using a slope of 0.7 was pretty good. Okay, so clearly there is a message here. There is a message that this graph of averages, when your scatter diagram looks like this, that graph of averages is coming out to have a slope equals r. And so we are going to look at that on our slide. So what we're doing is called linear regression now. We will apply this only in situations where the scatter diagram is linear, though in principle you could apply it in other situations as well. That would not be a great thing to do. In this situation, we have two variables, and it is very important to keep in mind that these have been measured in standard units. Otherwise, we have to keep track of what the units are, and we'll do that in a little bit, but we'll just look at the picture in standard units first. So what do standard units do? They are defining the deviation of your values from the center, which in standard units is 0, right? How far above 0 your values are. That's why negative values are below average values. Okay, and what we have said is our line, the gold points or the blue line here, those are the estimated values. Those are our predictions of y. Those measured in standard units are gotten how? By this equation. Let's look at this. This is the equation of a straight line. I'm saying this is the slope. This is the given value of x. What happened to the intercept? The intercept is 0 because, and here, let me go back to my pictures and see, do you see that they're all intersecting? All of these lines are intersecting at the origin. So there is no y-intercept. That is, the y-intercept is 0. So we have the equation is our predicted value is the slope times the given value. Everything is being measured in standard units. And so what is the slope? It is the correlation. This is the equation of the regression line, but the variables happen to be measured in standard units. Naturally, if we are going to do this kind of analysis, we are not going to always want to work in standard units. We are going to want to work in the original units in which the data are measured. But before we get to that, I want you to think about what this equation implies. Okay. Yeah, so what is meant by that is exactly what I'm coming to. So what is meant by this statement about average deviations? Okay. So what I would like you to think is, I'd like you to imagine is a situation in which you have two exam scores. All right. So you have midterm scores and final exam scores. And these things are going to be, imagine that their scatter diagram is roughly linear. And look at somebody. And so supposing we are looking to make a prediction for somebody, their final exam based on their midterm score, right? So let's take somebody who is 2 SDs above average on the midterm. This person did very well on the midterm, all right? So for that person, what is X in standard units? If they're 2 SDs above average on the midterm, X in standard units is 2, right? Question to you. Is your predicted standard units from the final exam equal to 2, greater than 2, or less than 2? Less than 2. Why? Because you're going to take your 2, which is the standard units for the midterm, and you're going to multiply it by a number. This is R. This is a fraction, right? It's positive. Midterm and final is going to be positive, right? That's a fraction. It's going to be less. And this is where the word regression comes from. Your prediction for the final exam is a little bit closer to the mean than what you started with. And so all of you people who did really, really, really well on the midterm exam, I'm afraid regression is not working in your favor. Let's just look at all of these people, right? So these people did really, really, really well on the midterm. Sometimes it is easiest to imagine the people who did perfect on the midterm. On the final, unfortunately, the only place they have to go is down, right? So it's no surprise that if you look at the scores on the second variable, where the first variable is very high, the average is somewhat lower. It's this dampening effect of the correlation that is called the regression effect. Your prediction for the final exam for somebody who did really, really, really well on the midterm is a little bit less good. Correspondingly, what about somebody who had a bad day on the midterm? They didn't do so great. What is your prediction for their final exam going to be in standard units? Are you going to predict the same in standard units or a little bit better? Better, better, pulls it up, right? The regression effect will pull up their score. And that is what is meant by, on average, y, the predicted y deviates from 0 less than x deviates from 0. Okay, so we want to talk about the equation of the line in original units. And you know what? I'm not going to do algebra. I am going to show you on a picture by using my iPad what is going to happen here. Actually. So I have a scatter diagram that looks kind of like that. And I've been drawing the picture in standard units, right? That point is what? That point is 0, 0. Okay. Now, what is my prediction line? If I tell you that this is X, then you are going to look at all these Y values and you are going to look at their center, which is somewhere here, right? And now your prediction is, it's a line, so it's a join the dots. And why don't I use a, that's your prediction, okay? Okay, and so what we're going to do is look at the slope of this line. This line has what slope? What did we say it was? Is it 1? It's R, slope equals R. So I'm going to draw this. I'm going to draw you a triangle. Actually, it's 11 o'clock. I'm not going to draw your triangle now. We'll pick up this discussion on Friday. Let me just stop here and take questions. We'll pick this up on Friday.